good morning, or evening. Mathematics contributes to our thinking and our actions every day. Now, mathematics is often perceived to be a difficult concept to understand as outlined by Lee and Schoenfield, and it is important for teachers to make sure their teaching aligns with all students' learning styles. One of the most effective ways to do so is by connecting mathematics lessons with real-life situations as outlined by Kaya and Kassan. Throughout this video, I will explore how mathematics connects to real life using examples of proportional reasoning, uncertainty and variation, and generalization, and explore solutions to these scenarios, as well as making connections to how Aboriginal and Torres Strait Islander histories and cultures can be acknowledged through the teaching of mathematics using the 8 ways of learning, as well as making connections to the New South Wales K-10 mathematics syllabus. Now, starting off with proportional reasoning. Proportional reasoning is based around ratio and proportion. The essence of it is understanding of multiplicative structure of proportional situations as outlined by Dole and others, which may sound confusing, but all it means is understanding the relationship between quantities. Furthermore, it is a concept that can also be applied to other primary school subjects such as drawing timelines in history or interpreting calculations in science as outlined by Dole. Let's start off with the application of proportional reasoning in real life. Say you're planning a trip from Sydney to London for 7 days. There are many costs to take into consideration, such as flights, accommodation, food, and miscellaneous costs for activities and shopping. This requires proportional thinking. It's important to consider that the costs for flights and accommodation are fixed costs, as they are upfront costs and cannot be changed. However, you are able to use proportional reasoning to budget for the other costs such as food and miscellaneous fees. We will explore the mathematical solutions on how to do so on the next slide. One way you can budget for your trip using proportional reasoning is working out the average in order to work out how much you can spend per day. Now, the costs of the flights and accommodation are fixed costs, which means they aren't subject to change. So we will calculate those first. As seen on the previous slide, the flights equate to a total of $2,888 for a return flight from Sydney to London. And accommodation equals to $1,611 for 7 nights, which equals to $4,499 together. Additionally, there are also variable costs, which are subject to change in this case. In this case, the variable cost is food, which is around $50 per day, which equals to $350 for 7 days. It is important to differentiate your fixed costs to help identify the base amount for your trip prior to considering your daily expenses. As seen here, I have broken them apart. Now that you are aware of your trip costs, both fixed and variable costs, it is crucial to account for other expenses such as activities and shopping by allocating a budget. Let's say, for example, you allocate $1,400 for miscellaneous costs. If you divide this by the amount of days your trip is, so 1,400 divided by 7, which makes your budget for miscellaneous costs $200 a day. Now, another approach to using proportional reasoning for budgeting is to set a clear limit for your food and miscellaneous expenses separately. For example, say your budget for the whole 7 days, excluding the cost of flight and accommodation, is $1,200. You can assign $350 to your food budget, as the average food is estimated to be around $50 per day in London, and the remainder of your budget can go towards miscellaneous costs. And your circumstances may change, so this can allow for unexpected costs and help accommodate that. So to calculate this, 12,000 minus 350, which would be 1,050 left, and then to calculate your remaining budget, it would be 850 divided by 7, which means it would be $120 per day, which allows you to budget more smartly and be more responsible with your spending. Now, the connection to Aboriginal and Torres Strait Islander histories. It is important as teachers to be inclusive, and teachers can do that without being tokenistic by integrating Aboriginal learning into their classroom. This can include the 8 ways of learning. An example of how it links to my example for proportional reasoning can be incorporating land links. By discussing the significance of Aboriginal and Torres Strait Islander lands in relation to the place you are travelling to give students a deeper understanding of respecting sacred sites they may visit on their trip. Now, in relation to the New South Wales K-10 mathematics syllabus, the mathematical application used for proportional reasoning in my example can be implemented into a Stage 2 and Stage 3 classroom as it relates to number and algebra topic, particularly additive relations in Stage 2, as seen when calculating the total cost of the trip, as well as using multiplicative relationships, which is referred to in Stage 2 and Stage 3 mathematics content area, as seen when working out the total cost per day and identifying the average cost per day using division. Additionally, this aligns with the New South Wales K-10 syllabus outcomes MA2 AR1 and MA2 AR02 in relation to additive relations, which was seen in my solutions earlier. It also aligns with the Stage 2 and Stage 3 syllabus outcomes for multiplicative relations, including MA2 MR01 for Stage 2 and MA3 MR01 for Stage 3, which you can see on the diagrams. Now moving on to uncertainty and variation. Uncertainty refers to the likelihood of what the single true quantity is, as stated by Begg and others. In more simple words, it refers to the probability of something occurring. On the other hand, variation or variability is all about multiple values a quantity has at different times or instances, also stated by Begg and others. A real-life scenario involving uncertainty and variation is when you are sitting the HSC exam. When a Year 12 student is preparing for their HSC, there is uncertainty about doing well in the exam or not being prepared enough. There is also a lot of pressure and uncertainty for HSC students, particularly if they need a certain score to achieve a certain ATAR. Let's say, for example, the student is aiming for an ATAR of 85. They would need to get a test score of 85 or above in order to do so. To work this out, we can calculate the score needed to achieve this. Now let's say X represents the score we need. The student identifies the average score as 65, so they need to significantly higher in order to achieve 85 or above. So now to work out X, we calculate X equals 65 plus 25, which equates to X equals 85. Therefore, the score they need a score of 20 marks higher than their class average in the HSC to achieve the ATAR they want. Another solution to work out the mark a student needs or identify their average mark to see how well their performance was is to calculate the mean score. For example, say there are 10 students in the class. The scores are 50, 55, 60, 65, 70, 75, 80, 85, 90, and 95. The equation we need to use is mean equals sum of all scores divided by the number of students. So you add all of those together, which equates to 725. So as seen here, the working out is 725, which is the total sum of all scores, and then you divide it by 10, which is 72.5. So by calculating the average score of the class, the student has a better understanding of the score they need in order to achieve the ATAR, as well as knowing their average score in the class and how much more they need to improve. The uncertainty and variation calculations used in my scenario can also be applied in a primary school setting as it aligns with the K-10 mathematics syllabus. As seen in these diagrams, which represent the content areas from K-6, the solutions and mathematical application I used integrated the Stage 2 and 3 topic of number and algebra, particularly additive relations, as seen when adding the test scores together, as well as focusing on representing whole numbers, as seen in the K-2 syllabus. However, in K-2, additive and multiplicative relations aren't explored until Stage 2 to 3. Additionally, the solutions used also addresses multiplicative relations. Furthermore, this also links to the New South Wales K-10 syllabus outcomes. As seen here in K-2, it addresses the outcome of representing numbers, particularly outcomes MA1, RN01, as well as MA, RN02. In relation to the connection to Stage 2 to 3 outcomes, the solutions I used in my uncertainty and variation example addresses additive relations, specifically outcomes MA2AR01, MA2AR02 for Stage 2, and outcomes MA3AR01 for Stage 3. Lastly, my solutions also integrate the syllabus outcomes for multiplicative relations, specifically in Stage 2, MA2MR01, MA2MR02, and for Stage 3, it links to the syllabus outcome of MA3MR01 as seen in the diagrams below. Lastly, I'm going to delve into generalization and how it applies to real life. Now, generalization in mathematics refers to a statement that is true for a whole category of objects, as stated by Dimitrescu, which refers to making a statement that is not just about an individual instance, but rather a statement that is supported by evidence or statistics. A real-life example of generalization is when cosmetic companies or toothpaste companies make the claim that, for example, as seen here, 9 out of 10 dentists say their product works, which is a general statement, as the companies only have results from 10 dentists, which does not give a very wide variety of results. It is important to test the validity of these statements and not to trust them too easily. Say, for example, you wanted to test the validity of this statement. You could do so by collecting your own data. You can choose a sample size of 50 dentists and create a survey asking them whether or not they recommend the product. After calculating the results, say 30 out of 50 dentists recommend the product, and the remaining 20 did not. After calculations, you realize that only 60% of dentists recommend the product in comparison to the claim. The difference in results creates more validity due to having a larger sample group in comparison to the smaller sample group. Additionally, you may choose to test the claim further with a larger sample group and possibly a different location. Say, for example, you test 100 dentists all over Australia. You ask them the same question: do they recommend this product, yes or no? And then you analyze the data. Say, for example, these results are 55 out of 100 recommended the product. So that means it would be 55 divided by 100 equals 55%, which still contradicts the original claim that 9 out of 10 dentists, and gives them more realistic result of the quality of their product. This links to the New South Wales K-10 syllabus in relation to K-2 and 3-6 content, as it focuses on statistics and probability, particularly data, as well as focusing on additive relations. In relation to the syllabus outcomes, looking at the diagrams here, it incorporates stage 1, 2 and 3 data content, MA1, data 02, as well as in stages 2 and 3. Overall, mathematics is all around us, as explored through my examples using proportional reasoning, uncertainty and variation, and generalization. I hope after this video you have a deeper understanding of these mathematical concepts in a real-life context, as well as how Aboriginal and Torres Strait Islander cultures being incorporated through our pedagogy, using the 8 ways of learning in order to create a supportive learning environment. Thank you for listening.